Good morning, class, and welcome to this lesson on Kinematics 12 projectile motion. Today we will be able to define projectile motion and learn some problem-solving tips, okay? So let's start looking at projectile motion, which is projectile motion is the most, excuse me, is the most common, projectile motion is the most common form of 2D motion. It is the most common form of 2D motion. So what is projectile motion? Projectile motion is motion of an object in 2D where there is no friction present and the acceleration in the y direction is equal to gravity and the acceleration in the x direction is equal to 0. Okay, so I will break these down and you will understand what this means. But projectile motion is motion of an object in 2 dimensions, so x and y. No friction. Okay, this is kind of common. This is like just like free fall. Similar to free fall. And the acceleration in the y direction is gravity, and the acceleration in the x direction is equal to 0. So let's look at the most common type of projectile motion question that, as far as AP Physics goes, is the most common problem we're going to see in whatever situation. In this one, it's a plane, okay, but it doesn't matter. So we have a plane. This plane has a package. This package is going to get released from the plane. Okay, this plane is going 115 meters per second. The question, very simply, is how far away? How far away on the ground? Okay, how far away in the x-axis does this thing travel? Okay, how far away does this thing travel? We know this plane is 10,050 meters high. Okay, so it's that high up. How far across the ground does it go before it hits the ground? Okay, so the first thing we have to do is realize that there is no friction present. Let's go back to that question. No friction present. So this package, when it is moving down, it's going to have an x component and a y component. X and y component. There is no force present. There are no forces present that is going to slow it down in the x direction. If you look at this picture, we notice it has a velocity of 150 meters per second, the exact same as the plane. Okay? The velocity is the velocity of the plane in the x direction. Okay? The velocity in x is 115 here, it's 115 here, and it's 115 here. The acceleration in the x direction is equal to 0 meters per second squared. So what is that saying? The velocity in the x direction is unchanging. The velocity in the x direction is unchanging. Okay? This thing will continue. This box will continue to travel 115 meters per second every second until it hits the ground in the x direction. But in the y direction, we'll call this y, in the y direction, gravity is pulling it down. So in the y direction, gravity is pulling it down. So we can see here, at this point right here, our velocity in the y direction was equal to 0. Okay, it was just released. Okay, it was just released. Over here, the velocity is getting bigger. And over here, the velocity is getting even bigger because it's accelerating down. It's accelerating down in the y direction. So we have to realize that very quickly. Projectile motion. X direction velocity doesn't change. Y direction velocity does. X does not change. y does. Okay? So, how do we solve this question? The biggest tip I can give you. Oh, here's another picture before we move on. Right when the box is released, it had. This is going to reiterate what I just said again. Right when the box is released, it had no velocity in the y direction, and as it fell down, the velocity in the y increased, increased, and increased because gravity was pulling it down. In the x direction, it stayed the same throughout the entire path. In the x direction, it stayed the same throughout the entire path. Okay, so there's a situation again. The one thing we have to realize, we're going to have, we have an acceleration in y, we have an acceleration in x. We have a velocity in y, we have an initial velocity in x. We have a distance in x, we have a distance in y. These are all separate, but the one thing that ties these two together is time. Okay, the one thing that ties these two together is time. Time is not a vector. Time does not have a direction. The time it takes for this package to fall in the y direction is the same time it takes for it to hit the ground in the x direction. Basically, it hits the ground at the same exact time in both directions. Okay, so time is the limiting factor. Time is the limiting factor. So that is our biggest problem-solving tip for projectile motion. The time in x, the time in the x direction equals the time in the y direction every single time. Okay, every single time. So let's start breaking this problem down. Okay, I'm going to start off looking at the y direction. I'm going to start off looking in the y direction. Okay. Why am I looking in the y direction first? Because y is the limiting factor. Y is the limiting factor. Because in the y direction, once it hits gravity is pulling it down. If there was no gravity, this thing would keep on going. Straight. It would just keep on going. Straight and straight and straight. It would never stop, okay? Inertia. But because gravity is pulling it down, the y direction is the limiting factor. So basically, let's start off with this equation right here. Y equals VOT plus 1/2 AT squared. Well, we know the initial velocity in the y direction, I'm going to put y's there. The initial velocity in the y direction is equal to 0. That cancels out. So this thing has to fall 1,050 meters. 1/2, 9.8 meters per second squared, t squared. Okay, so we have to solve for t right now. Multiply both sides by 2, divide by 9.8, square root both sides, and we get a t that is equal to 14.6 seconds. 14.6 seconds, okay? So this is our time in the y direction. This is not the final answer. This just tells us how long the package was falling for, okay? It was falling for 14.6 seconds. Now, right now, I want to point out another problem-solving tip. Be very clear on which direction is positive and negative. Positive, positive, negative, negative. Or, we can do positive, negative, positive, negative. Notice, in my equation right here, I said that 1050, it was falling 1050 in the positive direction. And because I called down positive, my acceleration here is also positive because the acceleration is pulling it down. I could have very easily went with a classic XY coordinate system and said, okay, it's going to fall down negative 1050, but that's also going to equal 1/2 negative 9.8 meters per second squared. Because if I call down negative, it's accelerating in the negative direction. So notice we get the same answer. It's still going to come out to be the same thing, but we have to be very clear, and this will show itself later. But just be very clear on what direction is positive, what direction is negative. Okay, so that's our second problem-solving tip. Our first one was time ties x and y together, and the second one is be very clear on which direction is positive, which direction is negative. So we know this thing falls for 14.6 seconds, okay? So our next slide is going to be very simple. if it's falling like this and the velocity doesn't change in the x direction, how far does it fall in 14.6 seconds? Well, this becomes very simple now. Velocity in the x direction equals 115 meters per second. Time equals 14.6 seconds. X equals what? What equation do we use? V equals delta x over delta t. Let me keep these the same. Okay. V in the x direction, so 115 equals delta x over 14.6. So multiply both sides, and we get an answer of 1679 meters, and I'm going to call that 1680 for significant digits. Okay, so this is the most common type of problem, whether it's a package falling off out of a plane or an object falling off a cliff. Basically, an object is moving in the x direction. It reaches some sort of ledge, and then it turns into projectile motion. So look at the problem-solving tips again. We had to take its velocity and break it down into two different components, okay? It was moving 115 meters per second in the x, but then it started accelerating in the y. So we used the y direction and gravity to figure out how long it was going to fall for. If we know how long it's going to fall for, and we know how far it's going, and we know how fast it's going in the x direction, if we know how fast it's going in the x direction, then we know how far on the ground it's going to travel in the x direction.